All right, welcome everyone. This is day 3 of all our classes together. So now we're starting a new unit called Dynamics, right? Our first and second class, we covered the unit Kinematics. And so our second unit will be Dynamics. So as you guys know, the first day of our unit will always be the content day. So today I'll be talking about like most of the content and information. And then the second day will be when we have the most fun, like doing Kahoot. And, it's really for you guys to have that fun and experience the physics we're talking about. So that's just an intro. And yeah, let's get started. So first, I'll be talking a little about what is dynamics, right? And then I know some of you guys have been talking about like gravity and things like that. So we'll go into forces and Newton's laws, and then also different types of forces. And if we have enough time, right, I might cover a little farther, and I'll leave some time at the end for Q&A. So what are dynamics? Okay, so dynamics, right? It's another word of saying like forces. It deals with, as you can see on the slide, it says deals with action of forces on matter, right? And in this unit, we'll be focusing more on how you can calculate certain mathematics using dynamics, rather than actually making those calculations, like the concepts, these formulas, where we get them from, rather than you actually solving it, because that would take a lot of time. So I would like if you guys can put in the chat, what do you think a force is? Okay, motion. Sorry. Okay, you might have seen it, but try to put it in your own words. What do you think a force is? Okay, yeah, okay. I kind of gave that one away, but I have more questions at the end. Something that makes something move. Yeah. Think of force as a simple term. You don't have to think of it as like a scientific term like osteoporosis or like, anthropology. You don't really have to think of it as something simple, something that happens to you in an everyday life. Yeah, okay, so I see most of you guys saying a push or a pull. That is correct. In physics, we really call a force a push or pull. It's not very detailed, a detailed explanation. Um, so if you can see my hands, right? I have a notebook right here, right? And basically, a push, if you don't know, is just pushing that notebook towards me. And if you're pulling, I have two hands right here, and I'm pulling this notebook apart. That's obviously not pulling because the molecules inside these notebooks are so tightly bound that they're resisting my force. Okay, so just a quick demonstration. So in physics, we describe forces using Newton's second law. If you don't know who Newton is, his name was Isaac Newton, and he was a physicist. Um, I don't know the exact date, but he was a physicist in the past, and he basically came up with these three laws to describe motion. So his first law is every object in a state of uniform motion will remain in that state of motion unless an external force acts on it. And note this word external, right? It doesn't mean you apply force and it moves. It has to be a net external force. And I'll more explain what a net external force means. So in the second law, it says the net sigma, parentheses sigma, force equals mass times acceleration. And in the image to the top, you see that F equals ma. You might have seen that in somewhere else. Some way I use to memorize this equation is just say FAM, like FAM, F-A-M, and you can also say F equals ma. So F represents the net force, or you can say net external force. And the sigma we use is a symbol. It's just like delta we've seen in kinematics, but it's a different symbol. It actually looks like this. It might look like a E, but it's like two inverse triangles. And that's a symbol in mathematics called sigma. And we use that to represent the net. It's kind of like delta, but it's like the sum or the net. You know, it's not really the change, but like the sum, the final sum. Okay, so basically he came up with this equation where m equals mass and a equals acceleration. He got this equation using calculus. So if you're interested, you can always go on YouTube and search up F equals ma derivation with calculus. But I won't be explaining it in this video. So his third law is every action, there's an equal and opposite reaction. And so basically what he means is, let's say I have a pen right here, right? So if I'm pushing this pen this way, right? Let's just imagine it. Imagine this pen is in this space that I'm in, and it's just floating like in a vacuum, right? I apply a force to it, and what is actually happening is this pen is also applying a force back on me. But because using Newton's second law, which is this equation, right? I know that I'm applying, let's say I apply 1 Newton to this pen to the left, right? And it's applying that 1 Newton back on me to the right at the same time. But because this mass is so small compared to my mass, right? I'm so huge and so big, you know, right? So my mass is bigger. My acceleration is actually very small. But this object has a higher acceleration. And in kinematics, right, we learned what acceleration is. It's a change in velocity. So basically, this object will start moving, but I will be moving back so at the small acceleration, right? This is kind of simple too, if you could think of it as taking a baseball bat, right? You're whacking a ball, right? That ball is pushing back on you when you whack it with the baseball bat, but because its mass is so small, right? Your acceleration backwards is so little, so small that you don't even notice it. But that ball just starts going into space, right? It just flings all the way where you want to hit it, right? So that's just a way I want you guys to conceptualize these equations, right? I don't want to just put all these equations and variables be like, oh, memorize this, memorize that. Try to think of it in your, conceptualize it, right? Imagine it, illustrate it, and it will help you understand these laws. So just to review, the first law is every object in a state of uniform motion will remain in that state of motion unless an external force acts upon it, right? In simple words, just, right? Let's say I have a calculator, right? And I just leave it on my hand, right? It's not going to move because every object in a state of motion will always remain in motion unless I apply an external force. And external force could be lifting it up, right, shifting it left or right, or just letting my hand go and it falls down. And also, this in my slide doesn't say this, but also if a object is in motion, it will also stay in motion. And I'm talking about velocity. So if an object is moving at 10 meters per second, right? A car is moving at 10 meters per second. Unless I apply an external force, it will basically drive along the road at 10 meters per second for forever, as time is relative, right? And the reason why you might think, oh, this is not true, right? Because if you have a car, right, and you're applying 10 meters per second, over time, it will gradually slow down, right? And that is because there's friction between the wheels, right? The bearings and the wheels. And it's so minimal that you don't really see it. But over time, that friction is a force. And it basically is a net external force, right? So all these laws, all these three laws kind of interconnect together. But definitely try to memorize these three laws and try to conceptualize it in your brain, right? How can I memorize and think of this, you know, and just think about these three laws suddenly? Okay, so let's move on. So there are four types of forces that I want to cover in these slides. So the first one is friction, right? Before I just talked about the wheel and the friction between the bearings and the wheel, and that is friction. I also have a demonstration here. So I got this box right here, right? And I have some sandpaper, right? And let's just take this notebook again, right? Which surface, just put in the chat, which surface do you think it will be easier for me to slide it across? The notebook, which is kind of smooth, compared to this sandpaper. Yeah, okay. All of you guys are saying the notebook. That's absolutely correct. And the reason why is because the notebook, right, its surface is so smooth compared to the sandpaper. And the sandpaper has, if you think of it as a microscopic level, if you look at it at a microscopic level, its atoms are kind of like zigzags, like cliffs, and then go up and down. And so basically, when I rub this box across it, right, the atoms on the bottom of this box are going to collide with those zigzags in the sandpaper. So basically, they'll get stuck, and you have to apply more energy, to just move this box across sandpaper. So the next force I'll be talking about is tension. Okay, what do you guys think tension is? Just put in the chat. Or give me an example of where you see tension in your life. All right, elastic force is not something that's going to be in AP Physics 1. Elasticity also is not going to be. Okay, pulling a rope, yeah, rubber band, that's kind of elastic, but yeah, you can have tension in rubber bands. Breaking a hockey stick when bending it too much, yes, that is a type of tension. Someone pulling a stick, yeah. So I think you guys get it. Tension is really just, right, I have a wire right here, and I'm basically applying a force with my right hand, and I have a force on my left hand, right? And I'm basically pulling in opposite directions, okay? You can also have, let's say I have some card right here and I'm bending it like this. That is also a force of tension because it's resisting the motion, right? If I let go, it goes back. Okay, so what do you think gravitational is? Think of gravitational. What is that word inside you see? Gravitational. Gravity, okay. I don't really see a Y, but okay. I was looking for the word gravitation, but gravity is fine as well. Yeah, so gravitational force is basically, right, you're jumping up and down and you basically get pulled back down because the earth is pulling on you, right? And remember we talked about that equation, net F equals ma, right? Because this planet, its mass is so big, so gigantic, right? That when you jump up, right? When you jump up, let's put just picture these two fingers are a person's legs, right? And this bottom flat, my left hand, is the earth's ground, right? When you're jumping up, you are applying a force downwards on the earth, right? Because we know that Newton's law said, Newton's third law is every object, right, that applies a force also has an equal and opposite reaction. So when I jump up, right, I am applying a force downwards, and this planet is also applying a force back on me. But because the Earth, its mass is so big that its acceleration is literally like almost near zero. So it doesn't really move, but you do. And that's why you go up. But because you go up, gravity also pulls you down. And so you basically come back down. So forces don't necessarily always have to be physical, right? You can have forces that are imaginary, like you don't see it with your visible eye, but they do exist, like gravity. Okay, what do you guys think the normal force is? Normal force. Okay, so think of it as Newton's third law. Remember I said how every object, right, that has a force has an equal and opposite reaction. Think of it as that third law. Okay, normal force is a chair pushes up. Okay, I like that example when you sit on a chair. Right, think of it as this, right? You need to have a force to have an acceleration, right? We saw it in Newton's second law, F equals ma, right? If your force equals zero, the net external force is zero, you have no acceleration. And when you have an acceleration, you move. So if you're sitting on a chair, right, gravity is pulling down on you. But what do you think is the external force, the counteracting force that's pushing, that's counteracting gravity? Okay, the chair is pushing, but I'm thinking of forces. Like, what's the name of that force that pushes you back up? Not really you. Okay, so let me just clarify, right? You're sitting on a chair, right? And you know gravity is, let me just draw this up. guys illustrate this. So, right, I have this person right here. Please don't judge my drawing, right? And you got a chair right here, right? He's sitting on there. His legs are like that. And we know gravity is pulling him down, right? Fg. But we know that he's not actually falling to the center of the earth, right? Normal. Okay. Sorry if I pronounced your name wrong. Rishiv Varshil. Yeah, it is. It is the normal force. And also Julie. Okay. Yeah, it is the normal force, right? Because the reason why we need this normal force, or we actually have to have a name for this force, is if we don't have it, we will basically be saying that you will get sucked into the center of the earth, which you aren't doing. And so you have this you have this normal force Fn, and because this force is in the positive direction, this force is in the negative direction, they cancel. So it becomes 0. And so we know that the net force equals ma, right? And if your net force equals 0, right, even if you have a mass, your acceleration is 0, right? So you don't move. Okay, just pay attention, right? Always, when you're looking at the Newton's second law, you always have to say net external force. I have to emphasize this because a lot of people, they said, oh, the force, what force are you talking about, right? There's so many forces, and what type of force are you talking about? It's the net, okay? So just watch about that. Okay, so let's start talking. So we talked about friction, right? It's a force that resists motion, right? And let me just draw this out for clarity. So, right, we have this surface, but at a microscopic level, right, sandpaper actually looks like this. It's like the zigzags. And so your box that you're shifting it along, its molecules are also very small. And these molecules are basically getting stuck in these zigzags. And so it makes it very hard to push along, as compared to as if you had a smooth surface, right? The zigzags are very, very, very minimal. So you don't really get that resistance. Okay? Let's move on. Okay, this picture to the left also explains what I'm talking about with the zigzags. And this picture to the right is something I want to move on to. Remember we talked about normal forces, gravitational forces, friction forces, and tension forces, right? So in picture A, you see this is what I'll be covering later, but it's called a free body diagram. And this free body diagram is basically this dot in the middle, this black dot in the box. And it's a way of like drawing things out for physicists because we can't have everything in our brains, right? We have to specify everything. And so the Fn is the normal force, right? It's counteracting gravity in diagram A. In diagram B, you have this friction force, right? I'm sorry, you have this applied force. So you're basically, you have a box, right? Right here. And you're applying a force with your finger. And because it's not moving, you have the static friction pushing it to the left. So it's like I'm applying a force, but it's not moving because I have friction counteracting. And that friction is called static friction. Okay, I'll cover more about what static is and kinetic friction, right? And the diagrams in the y direction, right? We have the Fn and Fg, so that's correct. So in diagram C, now there's a difference. So imagine I had a box, right, with the sandpaper, and I apply a force, but I apply it very, very small, that it doesn't move, right? What do you think will happen when I apply more and more and more force to the box? You can put it in your chat. Okay, so imagine I have a box, right, and I have it on the surface, right, and I apply, I start applying very, very small force, right, and it doesn't move. But I start applying more and more and more force. What do you think will happen to the box? Like, what do you think the box will do? Yeah, the box will be moving, right? And exactly what actually Jen said, the static friction will be overcome and the box will move. So static friction is something that we call per friction. So friction basically has two types of friction. There's actually static friction and kinetic friction. Static friction is actually larger than kinetic friction because it's like if I have with the sandpaper, right? And then I'm pushing it, but it doesn't move. But when I apply more force, it starts moving. Once it starts moving, it turns into kinetic friction. So basically the sandpaper and the box will have static friction at first, but once you reach that limit of static friction, when static friction can't take it, like static friction is like, oh, I can't take this force anymore, it transfers into kinetic friction. And that's why it starts moving. And because kinetic friction is smaller than static friction, right, you have a net external force. And that net external force is the reason why the box starts moving. Okay, let's move on. Okay, so just a clarification, right? To the top left, you have a equation, F of friction equals coefficient of friction times the normal force. This symbol right here, is something that we call mu. We pronounce it as mu, like mu. Okay, and it's a constant. It's like the higher the coefficient of friction, which is mu, the higher the mu is, basically the harder it is for you to push something across something. So basically, if you search up like a physicist textbook in like the friction unit, and they usually have like a table of like mu's, and those are like values that are already measured. So like you can have a mu of ice on ice, right? If you're shift on. Do you guys hear me now? Yeah. Okay. Sorry about that. Did you guys get left off on the equation part or the last slide? You just put in the chat. When did you guys hear me like stop talking? The equation? Okay. So let me just go over. So thanks for letting me know. So yeah, exactly, Pokemon Mew. Okay. So friction force, right? The friction force we use is equal to the symbol called mu, right? Pokemon Mew times the normal force. Okay. And the coefficient of friction, which is mu, is a constant. It's like, like a linear equation like y equals 3x plus b plus I'm sorry, y equals mx plus b, right? And then let's just say this equals 6. This b constant is literally what I'm talking about. It's like a constant. So there's different coefficient of friction. As I said before, right? You can have ice on ice, which is I believe 0.1 is the mu. You can have like wood on silver, and you can have like gold on magnesium. There's like different mu's that you can have, and those are like constants that scientists have already solved for, and it's basically like a constant. Okay, and so the n on the right is the normal force. So the reason why we get this equation, I can actually draw it out for you guys. Let's just say we have like a surface, right? And then you have a box, right? And we have downward force of Fg, right? That's our gravitational force, and we have a upward force, right? Of equal magnitude, which is Fn. And we know that we have a normal force because if there was no normal force, the box would just fall into the deep earth, right? And so F. Sorry. Do you guys hear me better now? Yes. Okay. 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 So basically, as I said before, you have a normal force and you have a gravitational force, right? And usually in AP Physics 1 questions, you have they give you like a flat surface. So you have no acceleration in the y direction. So you can always, you can usually assume that Fn is equal to f of g. So you can usually assume, I'm saying assume, if the acceleration in the y direction is 0, you can assume that Fn equals Fg. Okay, and Fg is equal to mg. The equation is mg. So m is the mass and g is the gravitational field strength. So remember last time I was asking like what is 9.811 meters per second squared, and you guys said, oh, gravity, but it's the gravitational field strength. Okay, so that's what the small g represents. Okay, so if Fn equals Fg, we can basically say that Fn equals mg. Okay, let me just move closer to my laptop if you can hear that better. Okay, so now we have, remember I was talking about static friction and kinetic friction? We basically have two different mu's. We have a mu subscript k, which means for kinetic friction, and we have a mu for subscript s, which means static friction. So always keep note of the units. That's why I said units are so important, because they show up. They are very easy to get mixed mash, and basically u subscript s is the mu subscript s is the static friction coefficient of friction. Okay, so on the right diagram, we see this graph of applied force versus friction resistance in newtons. So it's kind of like the force I'm applying in relation to the amount of friction that I get from that. Okay, so we see that basically, if you see on the right diagram, right, there's a top right diagram in that diagram with the 100 Newton box, right, and on a surface, right, and you're applying this force to the right, and that is your applied force. And so at one point, right, as you guys said in the chat also, the box starts moving, right, and so basically once it reaches this maximum peak, which is basically the maximum static friction, the amount of friction that it can no longer handle, it converts into kinetic friction. And between that shift between kinetic friction and static friction, it actually loses some energy. And so you actually see this drop right there. So basically you apply like 50, but then at one point it shifts down to 40. And basically kinetic friction will always be constant because it's like applying it, it's like I'm pushing a box, right? But then at one point friction is doing like constant friction is like applying a constant force against me, and that's what kinetic friction is. So don't get confused between static and kinetic. Static is when something is not moving. Once it starts moving, it turns into kinetic, and kinetic is always constant. The amount of friction that you get from kinetic friction is always constant, but static friction, that friction will change depending on the amount of force that you apply. Okay, the bottom left diagram. So the bottom left diagram is a free body diagram of static friction and kinetic friction. It's just to help you understand what I'm talking about. So basically you see, I'll just explain this really quick. So in static friction, right, your static friction is equal to your F of push. So your F net is equal to 0. And that's why the box doesn't move. But once you have a kinetic friction, which is when your static friction is basically your applied force is greater than your static friction, then you have F of K. And F of K is definitely smaller than F of S, which is static friction. And so your F of push is greater than your kinetic friction, and that's why you have this F net, right? F net, remember the sigma is just a symbol to represent the sum, or because I have a negative Fk, right, and I have a greater positive F push, the Fk gets subtracted from the F push, which gives you this F net. Okay. Okay, so next slide. Normal force, right? We talked a little about gravitational force, right? A box on the table, and then you have a normal force, right? Pushing up. So, but then we also have this normal force on an incline. So just because your surface is not flat doesn't mean you don't exert a normal force. Okay, so let's just have an example, right? I have this notebook right here, right? And right now it's vertical. It's not flat like a typical box on a table example, right? It's vertical. And I'm going to apply a force to it, right? When I apply a force to it, it's actually exerting a normal force back on me. But that normal force is not vertical like what you guys saw in the table example. It's actually horizontal, and it's opposing my the direction of my force. So I'm applying force to the right, and that normal force is applying a force to the left. And that's why this notebook is not moving. So similarly, on inclines, which are basically like angled planes, um, you basically have a normal force as well. And all right, let me just draw this out really quick. So you have a box, right? And we know that, so we're drawing a free body diagram, right? And the dot is like symbolizing the center of mass. Okay, so when we know that gravity always acts downwards, right? I mean, towards the center, but for us, you can just say downwards. So that's F of G, right? But you have this normal force, right? What do you think the direction of that normal force should be drawn? Should it be exactly going upwards? Should it going at an angle? Be specific in the chat. What do you think? How do you think I should draw this normal force? Okay, angle. All right, let's just say this angle is theta. I'm just representing as theta. Sorry, that's a really bad theta. But angle to, okay, so you don't know what theta is right now. It's just a variable. So you can't really say 100 degrees or 30 degrees. You could just say perpendicular to the angle of the incline. Yeah, it is perpendicular. It is, okay, so normal force is always perpendicular to the surface that that it has contact with. Okay, so you actually have this force going up like this, Fn, and this is perpendicular with this incline. Okay, so then now we have this Fn, right, going to the right. I mean top right, right, and this box is going to slide down, obviously, right? Because FG is pulling on it. But we also have this normal force. So sometimes normal force doesn't always has to be like flat, as you could think of a table to the left diagram. It can also be at an incline. But always remember that it's always perpendicular to the contact surface. So if the surface is tilted 30 degrees, 60 degrees, it's always perpendicular to that surface. Always 90 degrees. Okay, so now I'll talk about tension. So tension, as you guys have seen, it's like tug of war, right? You're applying a force in opposite directions. And you can also have an example of like a pulley. Like you have a weight on the bottom and you have a something pulling it up, right? The tension is going to basically resist that gravitational force. So, right, we have a bottom force of Fg, but because this ball is not just falling into, right, not falling down, we know that there's a tension force, and that tension force has to be equal in magnitude, but opposite in direction. Because remember, we talked about Newton's third law. Every object has an equal and opposite reaction, right? And also, if you guys learned about in the first class, like kinematics, right? There is no acceleration, so we also know that the net force equals 0. And also about vectors, right? A vector is a magnitude with direction, right? Forces are vectors, and so the net force is equal to 0, but their directions are opposite, and that's why they cancel each other. Okay, if you pull a drawer, let me think of this. You actually don't really experience any forces, because when you're pulling a drawer, it's actually accelerating towards you, which means like there really is no resistance. The only resistance I could think of is the bearings, like the wheels that run with the pulley. No, I mean the wheels, the bearings on the back that have like a um pole that you have on the side of a jar. That's like what allows it to roll forward. But not really. If I could think of anything about that. Okay. Let's move on. So gravitational, right? We also talked about that. Just a quick equation that you should know, right? Fg is equal to mg. This is your mass, and this is your gravitational field constant. So basically, if you're going on the moon, the reason why I asked you this question last time about a feather and a brick, right, on the moon, basically its mass remains constant, but because the gravitational field strength is so the gravitational field strength is like, oh my goodness. The gravitational field strength on the moon is so small compared to on the Earth, which is 9.81 meters per second squared, right? That's why if you're jumping up, right, it takes you like 10 seconds to come down because the moon is not really pulling you so strong. Yeah, exactly what James said. Okay, so let's move on. You should always memorize this equation, Fg equals mg. It will be very, really helpful um, in the future. Sorry, my computer is kind of lagging on me. Um, Wait, can you guys hear me? I feel like I just lagged out. Yes? Okay. Sorry about that, everyone. I think if you have any questions, my slide isn't working right now, but if you have any questions right now, just put in the chat because I can still see that and I'll answer it with my mic. Yeah, you have to take physics in high school. Or you can take AP Physics 1, which is basically what I'm teaching right now. But physics is definitely something that you have to take in high school. I mean, in New York, that's what I know. Okay, so helium uses a force called buoyancy. It's a buoyant force, and that depends on the difference in density. So you know, like so density is mass over volume. So let's say you have like a ice cube, right? You put an ice cube. You have an ice cube, right? You're putting it in water. Because the ice cube is less dense than the water around it, it floats up. So similarly, if you have a helium balloon, the helium inside is less dense than the air around it. So that provides like a net pressure because density is related to pressure, and that pressure basically pushes it up. I'm really sorry, guys, but my computer is still lagging. If you have any questions, you can put it in the chat. Okay, if my slides aren't working, that's fine. I think I'll just cover, go a little more in detail. So, okay, so remember I talked about the incline, right? If I have a pen, right, and I have a box, it's on an incline. We know that the normal force is applying this way and the gravitational force is applying down, right? So since this this normal force is a vector, right? It's a force. It has a magnitude and direction. And in kinematics, right, we talked about vector addition and vector components. So because it's not directly up, right, it's at an angle, it has an x and a y component, okay? And so the x component that we use with the x-axis, we represent that using mg cosine theta. Okay, I can't show you the derivation. I really wanted to, but my computer is still not working. Yeah, you have to split normal force into x and y forces. Yeah, you have to split normal force into x and y forces if it's at an angle. Actually, it's better to just do it anyways because it makes your calculation better. So basically, the x component of normal force is mg cosine theta. The mg comes from the force of gravity, which I'll show you later, and the y component is equal to mg sine theta. Okay. Sorry, I can't type in the chat. My computer is literally like just froze in midair. But I think the only thing I can do right now is just answer your questions with my mic. Like, okay, so I can't really stop share my screen because my entire screen is froze. Like, I can press stop share, but it's not going to stop share. Yeah. It's like my entire screen is just like my keyboard, trackpad, everything's done. Okay, Alt F4, I'll try that. It's not working. I think the only type of thing I could do is probably like shut down my entire computer. But are you guys fine with that? I mean, if you guys have extra time, I'm willing to make like a session. Like if you guys have like 30 or 40 minutes after 3 o'clock, like to 3:50, if you're fine, like I don't know if some of you guys have wave classes, but if you're fine with like missing like 40 minutes or something, that would be fine with me. Because the only thing I can think of is just shut my computer off. Oh, task manager and force stop zoom. I actually have a relatively new computer. It's a Windows 10 Dell Inspiron. I think it has like it's like running at a really high capacity, so it's just like closing. Okay, I opened up Task Manager, and trying to click Zoom meetings, but it's not closing. Off the slides tab. Wait, I think it's working. Is it? These are really unexpected times. If you guys have any questions, you can put in the chat. Meanwhile, I deal with this because I don't want to waste your time as well. Turn off the slides tab. Okay. Okay. So my computer just rebooted. Wait, can I search this? Okay, I managed to do that. Let me just reopen it again. Okay, so let me just share my whiteboard in the meanwhile. So remember I was talking about the incline, right? You have this box and you have gravity pointing down, Fg, and then you have this normal force, right? Fn. Okay, so I don't know if any of you guys have taken geometry, but this is how I'm basically going to show you how we get mg Fn x equal to mg. This is Fn y, is mg sine theta, okay? So let's say I have an angle theta right here. This is just a Greek symbol for theta, which is angle. And we know that alternate interior angles are all equal, right? If I have a transversal and these lines are parallel to each other, right? We know that this angle is also equal to theta. Okay. And we also know that this angle is perpendicular. Actually, let me just draw it out like. Okay, I'm not going to do this whiteboarding thing anymore. It's really laggy. Okay, so basically you have Fn x, right? The x component of normal force is mg cosine theta, right? And your Fn y, which is your y component of normal force, is mg sine theta, right? Okay, so let's say you have friction. Oh my goodness. So let's say you have friction going like this. It's opposing your motion, right? The way you would solve this problem would be basically adding all the x components of your forces. So you would have a Fx, and you also have a Fnx, and then you would find the sum, and that would give you your F net of x. And then if you're doing in the y direction, you would have to do a FFy plus a FNY. And then you have to put your FG, and that would give you your F and net y. And basically, after you find these sums, you could basically do a lot of things. You could find the acceleration of this object. You can find the time it takes for it to come down, and a lot of other things. Wait, is it still lagging? Okay, it's still lagging. That's really good. Okay, I think we have like 8 minutes left. So if you guys have any questions, just put it in the chat. I think that's the best way I can teach right now. I'm trying to open up my Google Drive right now, but that's still going to take me some time. So if you have any questions, just please put it in the chat. This is not the last day for AP Physics. Our last day is next Friday, August 20, I believe, 24th. Wait, no, August 28th. August 28th is our last one, because we still have one more unit after this. It's two classes per unit, and we have 3 units, so that's 6 classes. Yeah, if you want to go, it's fine. I'm just trying to open my docs right now. My slides, I'm sorry. Okay, never mind. I got my slides. Okay, so now I'm just going to talk really quick. So basically we have I think in the first class you guys talked something about momentum. You asked like a question about momentum, and then we also have this term called inertia. So inertia is more of like a resistance, right? Like let's like the example to the right, right? If you have a car and it's stopping super sudden, but it's like it has a velocity already, you have a inertia, and basically that inertia basically causes you to lunge forward, and that's why we have airbags. Okay. And in AP Physics 1, inertia just depends on mass. So the higher a object's mass is, the more inertia it has. And it means like it's harder to stop this object from moving, from not moving, okay? And then momentum is different. Momentum is like how much motion I have. So if I have a big momentum, it's like saying that I have a lot of like motion in me. Like this object has a lot of, I think you could think of it as like energy. Like I have a lot of energy, and that's why I have a momentum. Inertia is different. It's like how hard it is for me to stop something. Okay. Um, and then we have this called static and dynamic equilibrium. Okay, so static equilibrium is when something, some object is not moving, which means that its acceleration is equal to 0. Okay, it means literally that this object is not moving, like stationary. Okay, And then you have dynamic equilibrium. Dynamic equilibrium is when your acceleration is also equal to 0, but your velocity, you have a velocity. So I can be running at 10 meters per second, right? But I would be at dynamic equilibrium if I don't accelerate. Whereas static equilibrium is like if I have a box on table, right? It's not moving, it's doing nothing, and it's just static, like not moving. Okay, so these are two different types of equilibrium. So you can technically have an equilibrium if you're moving or if you're not moving, as long as your acceleration is always equal to 0. Okay, so this was while I was talking about inclined planes before. So basically, I don't think I have time for a derivation, but basically your your force of gravity basically can break up to, I'm sorry, your normal force can basically break up to x and y components. And so um, your normal force could be having a x component downwards. You can also have a y component. I'm sorry, you can have x component going to the left, and you can also have a y component going downwards. And this is really important because basically what you can do with normal force is you can use it to solve for friction. So basically, remember we said that friction is equal to m is equal to the normal force times mu, right? The coefficient of friction. So if you find your normal force, you can basically find your friction force by just multiplying it by the mu. Okay. Okay. So let me just go over a little about free body diagrams. So you guys probably saw me drawing last time about like a dot, right? And then it has a force up and a force right. And basically, this is the way that physicists or even students in AP Physics 1, this is how we represent what's happening to an object. So if an object has velocity, or it's moving, you don't have to draw a free body diagram for it because it can technically be in dynamic equilibrium. But once that object has an acceleration, which means that it's not in equilibrium, then you have to draw a free body diagram for it. Okay, so let's just say I have a car, right, and it's moving this way at an acceleration of 2 meters per second squared, and its mass is equal to 4 kilograms. Okay, so just type in the chat, what do you think this force would be? And also, what other forces should I draw for this car right here? Okay, no problem. So the question I was asking is, what is the force, this force, the magnitude of this force? And also, if there are other forces, how should I draw it out? Like learning about gravitational forces, frictional forces, normal forces, things like that, applied forces, 8, yeah, 8 what? What's the units? You have to be specific. Like I can say 8 like pounds, I can say 8 kilograms, but you have to specify what's the unit for force. Think of it as like Isaac Newton. Newton's, yeah, it is Newton. So in physics there's something called derived units and SI units. And SI units are like, they're like, derived unit is more of like a basic unit, and then SI unit is like, it comes from being like calculated. So basically what happens is kg, right? When you take mass and you multiply it by acceleration, it gives you force, right? And so you could basically say kg times meters per second squared equals your newtons. And this is a key unit that we use for force in AP Physics 1. Okay? So we have a force of 8 newtons. Okay, what other diagrams do you think I should draw? What other forces do you think I should draw? This, just to clarify, this car is driving on a road. Uh, let's just say friction is negligible. Think of like gravitational forces and normal forces. Okay, it has a gravitational force. What is its gravitational force? Assuming it's on Earth. 9.8 meters per second. Okay, remember I talked about Fg equals mg, right? Your g is equal to negative 9.8 meters per second squared. But you also have to multiply that by the mass, right? Because that's what gives you the force. So if you take negative 9.8 and you times it by the mass, what's the force that you get? If you want just for calculation purposes, you can just round 9.8 to 10 and just do 10 times the mass. 39.2. Yeah, okay. Yeah, it's around 40. I would say around 40. And if you're assuming 9.81, like usually some people, they just assume 9.8 to be 10 because it's better for calculations. You can just do 10 times 4 and that gives you 40. So I'll just write 40 here, but 39.2 is correct. Okay, what other force do you think there is? Right, now we have a downward force of Fg of 40 newtons, we know that. And we have a right force, applied force of 8 newtons. What other force do you think there should be? And we know that this car isn't, right, it's not getting sucked into the middle of the planet, right? There has to be some force counteracting that. Normal, exactly. What magnitude do you think that normal force should be? Like what amount, how much of this normal force in units of newtons? 40, exactly. 40 positive or 40 negative? Positive. Yeah. So I think you guys basically get it. This is basically how we do free body diagram calculations. And basically what we do is if we don't know we don't know how to solve this problem, we always draw a free body diagram in the beginning. Okay. And this free body diagram will help us illustrate what is happening to this problem, this scenario. And then using this, we will then make our calculations. And also when you draw these free body diagrams, please keep note that how long you draw these arrows also matters. So the longer you draw it, it means it's a greater force compared to your other forces. Okay, so length also matters. So um, that's about it for me for today. Sorry if you guys missed a lot. I'll try to cover more of them. Get what I didn't cover in the next one. And in the next class, we'll be doing more practice questions and also Kahoot. So it'll be more of like a fun day, and I'll try to find some simulations as well. If you guys have any questions, feel free to put it in the chat, and I'll stay until the last person leaves.